So I would like to welcome you back at our distinguished seminar series here at the Energy Institute. And today it gives me great pleasure to introduce a very close colleague and a person who has been working for many years, an expert, a distinguished expert in the area of oil and gas, and with particular focus on demystifying the role of hydrates and the important role that they play in the gas extraction. And now he's looking very carefully on the opposite problem, how we can take advantage of in the CO2 sequestration problem, and as part of Aquifers, a subject that he's going to talk about. So it is Professor George Moridis, who is a professor of petroleum engineering and holds the Robert L. Whiting Chair in Unconventional Resources here at Texas A&M. I'm very pleased to say that George is a chemical engineer, of course, so from the National Technical University of Athens, Greece. And then he came to Texas A&M, as a premier institute for petroleum engineering studies to do his master and PhD studies. And then, he went on, on a career path, which has included a very distinguished time within the Lawrence Berkeley National Laboratory, where he was a senior scientist and head of the hydrocarbon research program in the Energy Geosciences Division since 1991 when he joined. And he particularly looked into, as he established a very strong program on unconventional resources, for hydrates, the shale gas, and the revolution that we experienced in the shale gas era in connection, obviously, with oil. And he led, and one of his key expertise, and he's going to talk to us about, I hope also, he's an applied mathematician. It's like a simulation type person. Also, he develops simulation codes to study these sort of very complex systems where, we have fluids with solids and, in many directions, he will demystify to us a little bit. And he's really has developed this tough initially hydrate and tough to, so it's a software system, a simulation system for especially studying on the hydrate, a subject that is very close to his heart. He really was he was a senior faculty associate there. He held also the ExxonMobil Visiting Professor Chair at the National University of Singapore from 2015 to 2018. And what I would like to also mention is that he has received many accolades through his career, and with some that I would like to mention, he's received recently, last year in July of 2023, the Lifetime Achievement Award by the Scientific Committee of the 10th International Conference on Gas Hydrates at a conference that was held in Singapore. He was a distinguished lecturer of the Society of Petroleum Engineers and has been a distinguished member of that society since 2010 and became an honorary member, something that is very really, only a very, very small fraction of people can become. So he holds also various prestigious visiting positions in many parts of the world, including Turkey, the Colorado, US in the Colorado School of Mines, as well as the Chinese Academy of Science. So it gives me great pleasure to introduce Professor George Moridis, who is going to demystify for us CO2 sequestration aspects in the context of Saline, Aquifers, and many more. George, so please join me in warmly welcoming Professor George Moridis.
Thank you very much. Let me leave my display here. Thank you for the very generous introduction. As you may have noticed, the title is different from the one that I initially submitted a long time ago. And the reason is that since I submitted this, I did quite a bit of additional work, and I thought it would be a great idea to discuss this and share this with you. So instead of focusing just on vertical wells, the title now is Factors Affecting the System Behavior and Practical Implications for CO2 Sequestration in Saline Aquifers using Vertical and Horizontal Wells. And there is a very good reason for that. So why is this not moving?
Press it on the.
Okay. So the presentation includes, first of all, a statement of the problem, discussion of the objectives, then a very short discussion about the simulated system and the code, some reference cases, sensitivity analysis, and then possible mitigation of halide precipitation. In case you don't know, halide is the precipitated salt, okay? And some results and conclusions at the end. So what is the problem? Whether we like it or not, it is extremely unlikely that we will try to inject CO2 into potable or freshwater aquifers. Freshwater is a very valuable resource, which is becoming increasingly rare. It is used for municipal purposes, and the majority of people do not want to drink soda water. They want to drink water. This being the case, inevitably, we will focus on saline aquifers, which are deeper. That's why they're more saline, longer time exposure to minerals. In addition to this, they are of little use in terms of municipal applications. Salinity is expected to be a very serious issue because of injectivity eliminations that are caused by halide precipitation. And I would like to quote a statement by some early pioneers in this study of the study of CO2, and that's Miri Halavan, who stated that little success has been achieved on the quantification of the expected impact on the formation injectivity and near well pressure buildup. And this is exactly what we're focusing here. And I will be more specific about how this is approached in the next few statements. So what do? We analyze the impact of salinity on the attempt to store CO2 in saline aquifers, and we investigate how to do that using both vertical and horizontal wells. The way it works is that we inject into the system until a maximum allowable pressure. A good rule of thumb, actually, it is part of the rules in just about 50 states in the US, that the maximum allowable pressure should not exceed 65% of lithostatic pressure. After that, we let the system rest for 100 years. Well, actually, I went up to 1,000 years, but what I found out that after 100 years is very, very smooth from that point on. So there was no need to do that, especially because these simulations are very long. We evaluate different well designs that can materially affect the sequestration performance, and we do find that, yes, the well design can be a critical factor. We evaluate the relative importance of factors and conditions that can affect the precipitation and the overall sequestration performance. And if we have halide precipitation, we investigate some methods to avoid those. Now, what is the system? What you're seeing over here is basically two different well configurations in the vertical well description. The system, the well radius is the domain radius about 500 meters. On the left-hand side, you see case R. The reason I used the R is because to me initially that was the reference case because it made the most sense. So what you see over here is that we have an aquifer which is 50 meters thick, but we have the perforated interval of the well only 10 meters, and this is at the bottom 10 meters. Why is that? The logic was the following. What we want to do is exploit as much as possible, not only the sequestration potential of the system itself, but also the sequestration potential that comes with the solution of CO2 in the water. Because CO2, relative to other gases, dissolves in relatively very high amounts. What do we need to do that to maximize that? Well, we need to make sure that the water comes in contact with as much of CO2 as possible. So we inject at the bottom. And because of buoyancy, this will rise. So this will give us theoretically or expected the best performance. That's why this was called the case R. Now, in addition to this, what we investigated is two different cases where the well is completed the entire 50-meter interval. But there are two different ways of approaching this. One is, and you look at there over here, you inject at the bottom. It's exactly what you were trying to do in the previous case, but now we have the quote-unquote disadvantage that the well is open, so the fluid, CO2, will follow the path of least resistance, will rise on the well and come at the top too. So it's not going to be as effective, at least in our initial thinking, than just using a short well. In the other case, we inject at the top. Now, what we use is a very fine domain discretization. The domain is about 104,000 elements, which means about over 400,000 simulation equations. The discretization is very, very fine. One of the problems you will see in the literature, and that's why there was this discussion, this early comment by Miri and Haviland, was that the grid blocks are usually no smaller than a meter. This being the case, if there is salt, basically because of average over large volume, this disappears. We don't see any precipitation. This basically means that in our simulation, the vicinity of the well has extremely fine grid block size, talking about millimeter, about 5 millimeter, all right? And then millimeter to centimeter until at a minimum of 20 meters from the well. And after that, of course, then we use logarithmically increasing grid block size. Now, in addition to this, we use the equivalent horizontal system. What I mean is that we used a horizontal system that would inject the same amount into the aquifer, which is supposed to be 50 square kilometers, that the cylindrical system would do. I don't want to spend very much time on the specifics here because that would be quite boring. Let's just say that initially the pressure is about 200 bars, which basically means this is a system about 2 kilometers deep, which makes sense. The initial temperature is about 68 degrees, and we inject at the rate of 0.2 kilograms per second, which corresponds to about 850 kilotons per day. This is exactly, 800 tons to 1,000 tons per day is what we expect to have as a reasonable injection rate in most cases. The overburden, which means the gas cap, well, we assume has permeability of 1 nanodarcy, but this one is one of the variables we investigate, the importance of which we investigated. And the permeability of the system is about 200 millidarcies. In the cases where we needed to inject some water to dissolve the salt, the injection rate was only 5% of that of water. And these are the basic things we'll discuss. The simulation code is the TAF Plus code, version 1.5 with a real gas prime. This is the code, the flagship code that we developed at Lawrenceburg National Laboratory. This has been used by about 400 organizations in about 70 countries all over the world. And as you can see over here, the option is 2023. Actually, in 2024, a very good student of mine developed the parallel version, which allowed us basically to conduct these simulations much faster. So what you're looking at over here is the 4 reference cases. Case R, short well. Case L, long well, but we injected the bottom. Case T, long well, we injected the top, and horizontal. What you see also is the reference salinity. We use a 2% salinity, which is pretty low, but this is the basic. This is what we began with. Now, what it takes is a certain period to reach the maximum pressure. And that's what you see in this column over here. And that ranges from 18 years in the case of R to about 23.36 in the case of T, which is at the top. The horizontal well is beginning to show its advantages. It takes 33 years or so before we reach the maximum pressure. Now, the next column over here is how many time steps it takes to reach that 18 to 33 years. You can see it can be hundreds of thousands of time steps. And after that, you see the total simulation time and the total number of time steps. By the way, this is by no means the highest possible number of iterations of time steps you need. In some of the cases of high salinity, I reached about close to 1 million time steps to cover about 100 years, 120 years. So some of these simulations took months to complete. Continuous execution time, initially on a fast workstation. Now it takes months actually on a supercomputer, on our supercomputer. So the time to reach the maximum allowable pressure is the TIE, and this is defined as 65% of the hydrostatic pressure. This is actually the rule in most geotechnical cases. All right, what we're looking at over here is the performance of the four cases, the four reference cases. On the left-hand side, you see the injection, the pressure evolution in the vicinity of the injection point. So, and the lines over here are the ones that define the maximum allowable pressure. You can see that case T, which is basically the top of the injection on the top, reaches case R, which is the black one, is the one that reaches that maximum pressure the earliest. So we're beginning to see that injecting in a short well at the bottom does not appear to be that good. And the other thing is that the one that takes the longest to reach the maximum pressure is the one, the horizontal well. This is the green curve over here, which is an early indication about the advantages of horizontal wells. And if we see the evolution of pressure afterwards, which you can see in the B over here, in this curve B over here, this is basically showing you how the pressure develops once we stop injection. This is the rest or idle period. Now, and this takes 100 years. You can see that there is a decline in pressure. However, this decline is quite gradual. Keep in mind that the overburden pressure is 1 nanodarcy. So, you would expect that the pressure dissolution would be slow. But what you can see is that the pressure is maintained at pretty high level for very, very long times, which means that you cannot go back after 5 years and say, I'm going to re-inject again. Okay, it appears that once you do that, then you cannot inject anymore. What is very interesting is the graph that's next to it, and that is the evolution of the halides in the system. Now, this halide, as you can see, concentrates within the first 10 centimeters, no more. You're not going to see any more than that. It is like a glove, and if it's there, it can stop injection. If it's not there, it can go forever. What you see is, first of all, there is a very rapid increase in the amount of halide that is precipitated. Yes, the system gets dried out, injects CO2 at high rate, it dries out. Now, this creates capillary pressure, which draws more water, and that water still evaporates, so keep accumulating. Then, when we stop the injection, and you can see that the top of this very steep curve is the end of the injection over here. There is initially a precipitous drop. Makes sense, because we stop injecting, so the pressure now in the system begins to equilibrate. At the outer reaches now of that halide precipitation, there is fresh water coming in, and that dissolves that very low saturation of initial halide. And that lasts for a while. After that, we can see this at least in the black curve over here, the R. We can see that there is a period, at least in this case, of very gradual decline. This is when we have basically the effect of molecular diffusion. After that, there is a precipitous drop, which is, you can see this best in the black curve. This is when we have significant dissolution of CO2 in the aqueous phase. CO2 dissolves, and unlike other gases, when CO2 dissolves in water, the density of water increases. So now this creates now convection cells, and that accelerates dissolution. And this is what you see in the black curve over here, case R. Look at the blue one. This is case T, where we inject at the top of a long well. You see there, because of the configuration of the accumulation of the halide, we have the effect of these convection cells from the beginning. That's why you see this early decline. You also, this shows you a significant advantage of the top wells, okay, that salt dissolves much easier in this case. And you also see the very significant disadvantage of an L well, where the well is long and you inject at the bottom. What you see happening is that molecular diffusion does not appear to have a very significant effect. And looking at the curve, the red curve over here, you can see that also, for some reason, we don't develop these convection cells in this case. So this is a very serious disadvantage, and you could see this more explicitly in the future. The other very important thing you see here is that red comment at the bottom. There is no halide precipitation in case H. What is happening is that we inject the same amount over a much longer total well length, so the injection rates are much milder. This being the case, we don't create this drying effect. The drying effect, which is no more complicated, you drop a drop of water over here and things start blowing on it. What happens? It dries. Why? Because we keep replacing the air with slower in water vapor. Well, the same thing happens here. The flow rate is low because distributed over a much longer length of well, so we don't have any halide precipitation. So perhaps you can begin to see why I was interested in showing you the results of the horizontal wells. Now, this can be complicated. However, on the left side, you see how much CO2 we store in the system. On the right side is how much we lose. So let's discuss one at a time. On the left-hand side, the green curve is the horizontal well. The solid line at the top is the total. And you can see that this exceeds everything else. In addition to all the benefits I've seen up to now, you can see that we can store the maximum amount for the horizontal well. This solid line is composed of two lines. There is this line over here, which is the dotted line. You see this over here, the green one at the bottom. This is how much is stored as dissolved CO2 in the aqueous phase. And what you see is that amount keeps increasing over time. The other thing you see is that the other green curve is that curve over here with two dots. And that is how much is stored in the gas phase. And you can see, especially after the end of the injection, which is basically where you see that sharp change over here, the amount that is stored in the gas phase keeps going down. Why? Because CO2 keeps dissolving in the water, and what is dissolved in the water keeps going up. The sum, the total, is practically constant over 100 plus 133 years. The same happens in all other curves. So in terms of relative importance, what you see is the green curve, which is horizontal, is better than the next one is the T well. Injection at the top. Close behind, for the 2% case only, the reference case, is the L well at the bottom. And the R well, short interval at the bottom, is the one that has the probably least desirable performance. This is good and great. What is also very important is how much of the CO2 is stored in the aqueous phase. Why? Because the amount of water we have is humongous. This being the case, that basically means is that it's a resource that we need to maximize. We try to dissolve as much water. And you see here another significant benefit of the horizontal well. So at this point over here, about 33 years, you can see this where my arrow is. This is the end of injection. And then you can see that continuously increases. And at the end of 133 years, about 55% of the water, of the CO2 we injected is dissolved in the water. Fantastic, that's what we want. In the case of all other wells, you see the amount is much less. Okay, so the next thing that we need to discuss is what leaves the system? What is This is the water actually, sorry. What kind of water losses we have in the system? Why is this important? Well, it is important because what we want to do is we want the water that existed in the aquifer to leave. We don't want the gas to leave, the injected gas to leave in the system. And what you see in this case again is that the one with the best performance is the horizontal well. This is the green well over here. Okay. Now we see a clear superiority of the horizontal well. Here is, sorry, I misspoke before. Here is on the left-hand side the losses. Again, the solid curve is the total losses at the top. Okay, and the total losses basically involve two components. Let's look at the green one. This one here is the total loss over here in the horizontal well. This is basically the sum of two things. This is the total loss in the gas phase, and you can see the gas phase loss is much larger than the loss in the aqueous phase. So, well, to be expected in that case, what we do is we inject, the CO2 accumulates at the top. So it is that leaves, and some of it also is expelled with the water. Great. And you can see the same pattern everywhere. The solid curves are the total losses, and the behavior is the horizontal well in terms of losses, the absolute losses is basically about the same as the T well. However, this does not describe the full picture, because the full picture is what percentage of the CO2 we injected is basically lost. And you can see that in this case, the green one curve over here, which is the one below B, shows you that the green one, which is basically horizontal well, has the smallest losses in terms of percentage. So after about 133 years, we've lost a grand total, which is less than 0.8%. 0.8%. The other thing you can see that in all these cases, case of H, T, L, and R, we more or less don't exceed 1% of total injected CO2. So this is pretty good. We like it. On the right-hand side, I'm just showing you including this to show you the kind of variations you would expect in the terms of Q, the release rates. Some of this is caused by, of course, discretization issues, and some of this is also caused by the fact that we need to build up sufficient amount of gas to overcome the reducible gas saturation before the gas can move. Okay, that's why you see some of this kind of oscillatory thing. I'm not going to spend any more time on this because, again, this is not where the story is. Let's look at what happens now. What we're looking at over here is, on the left-hand side, is the gas saturation. This one here, the first one on the left-hand side, is for case R. We inject at the bottom. So we inject at the bottom, CO2 rises up, reaches the top of the aquifer, and then starts expanding. Do you see that? The other thing you see very interesting is until the end, the injection point, which is highlighted by the high saturation, which is the red color over here, stays at the bottom. This is during injection. Next to it is case L, where we inject at the bottom, but we have the total well open up. What you see very early on is that, yes, we inject here, but you can see that gas arrives at the bottom at the top very early because the wellbore is open. It's almost an infinite permeability highway. The other thing you will see is this. Look at the injection point, the red area over here. What is it doing? It's moving up. Why do you think it's moving up? Because of halide accumulation. You inject at the bottom, halide begins to build up at the bottom, so the injection point keeps going up. This is the reason for that. So this is during injection. Left on the right-hand side here, this is the third column over here. This is what happens when we stop injection and we wait for 100 years. What you see happening is that the gas will accumulate at the top and will spread at the top. At the same time, you see that the saturation, especially that near the bottom, will go down. Why? Well, because it dissolves. First of all, some of the gas keeps going up, and then some of it dissolves. Okay, so that's why the free gas goes down. And you see something similar in the case of R over here, case L next to it. Now, What is very important is for us to see what happens to the case of dissolved gas. And you see happening something very, very interesting. Here is during injection. Again, case R, we inject at the bottom over here, and the footprint of dissolved CO2 in the aquifer is more or less a mirror image, or actually it follows very closely the amount of free gas in the system, because again, this is pretty quick, it's a dynamic event. Molecular diffusion does not have much of a chance to be really effective in this case. So more or less, if you compare the footprint with the footprint of free gas, they more or less match. And you also see that, as a confirmation of this, you see how steep the front of the dissolved CO2 mass fraction is in the system. Look at this over there. It's within, we're only able to capture this because we have this extremely fine discretization. So within a few centimeters, basically, you go from the maximum amount of dissolved gas, which is the red, obviously, which is the solubility limit of CO2, to nothing, okay? Now, and you can see the same thing in both the case R on the left and case L, the long well injection at the bottom. What is very interesting, what's happening during injection, because what you see is the emergence of these stalactites. There is stalactites below the accumulation of gas at the top, and also there is development of a toe at the base of the system. Why is that? Because this is when we dissolve a lot of CO2 in the aqueous phase, and now we begin to create a water which has higher density, so we begin to see now the drainage of these things, the creation, the beginning of these convection cells. And this is the reason why this is why we have the evolution of the stalactites here in both cases, and also why the toe begins expanding at the base of the aquifer. All right? Now, what is very interesting is what happens to halite accumulation. On the left-hand side, again, is case R. Keep in mind that this covers only 10 meters on the left, which is the area, which is the length of the well. You also see that basically we have this happening over 15 centimeters. If you have a meter or even half a meter grid block, you're never going to see that. So we can capture here the evolution of the halite right next to the well. What is very interesting is what happens with the case R, the case L, which is basically the long well injecting at the bottom. What you see happening now is that you begin creating halite not on the bottom where you inject, but also at the top. And the two approach each other from different ends, and eventually they collide and they create a solid, very uniform globe of halite around the well. Okay? Why is this important? In the first case, what is happening now is the system is asymmetric. We have a 10 meters thick or long system of halite, which, however, is not symmetric enough. So there is an asymmetry in the system, and this helps diffusion and also helps dissolution. And this is the reason why about 70 years, all of this is completely dissolved in the case of our well, short well injecting at the bottom. Look at what's happening in the very symmetric case on the right-hand side, the case L. We have a very symmetric case over here. There is no kind of imbalance in the system. So this stays practically unchanged. We can see how the well design can have significant effect in this case. All right. Now, we discussed cases R and L. Let's discuss what happens to case T and H. T is basically the injection at the top. What you see happening is that, similar to what we saw in the case of L well, the injection point, here is the gas saturation. On the left-hand side, the injection point starts moving down. You see that? And the reason it starts moving down is because, again, we start building halite at the top. In the case of the horizontal well, it's a different situation. You can see, first of all, the footprint is much wider. Okay, it expands, it moves out in the horizontal direction, And this is one of the reasons why we have so much more CO2 dissolved in the water in this case. And we inject at near the bottom, and this moves up. And if we stop the injection and we move now to the right side of the panel, what you see is that in the case of the T well, of course, the footprint of the free gas keeps shrinking because of buoyancy, in addition because of the solution, and we have accumulation at the top, which makes sense. And the same happens in the case of the horizontal well. And similarly, I mean, what you see over here is what happens to dissolved CO2 in the aqueous phase. Again, you see the same pattern on the left hand during injection on the left hand side. More or less, the footprint of free gas is the place where we also see the footprint of maximum or dissolved CO2, which makes sense. But what you also see very, very clearly on the right hand side is the stalactites. Now, as we begin to have the effect of the creation of these convection cells, and also the development of the toe at the base of the system. Okay, but what's really interesting now is the very different evolution of the halide. First of all, there is something in red letters up there. No halide in the case of H well, horizontal well, no halide at all. The vertical well, what you see happening is the halide concentrates at the top of the aquifer. And at this location, it maximizes the convection cells. And that's why on the left-hand side, you see what happened during injection. This keeps building up. Right-hand side, you can see how it shrinks. And this explains this continuous decline line. Okay. So, well, sensitivity analysis. We checked a few things. Number one, this is the TIG wells now. We see that TIG wells appear to be behaving the best in terms of vertical wells. So we check a few things. Number one, we decrease the permeability of the reservoir by a factor of 4. So instead of 200 millidarcies, that's 50 millidarcies, and that is the green curve. Then we increase the permeability of the overburden by 2 orders of magnitude. So instead of 1 nanodarcy, now it is 100 nanodarcy, which makes sense. Okay. The other thing we do is we increase the injection rate by a factor of 5. So the behavior in terms of the evolution of the well, I mean, you get a pretty good idea where the sharp point is that, the earliest arrival at maximum pressure is we inject at 5 times the injection pressure. It makes sense. But the very interesting thing is that this is associated with what? With less halide than the reference case. Why is that? Because there is a sweet point, quote unquote, of capillary pressure. If you inject at very, very high rate, you basically completely dry the vicinity of the well, and the velocity of the fluid is sufficiently high to not allow water to come back by capillarity. And this is the reason why we have this one over here, the black curve, which is the halide associated with the high injection rates, being much less than the reference, which is the red curve over here. The other thing you see is that the amount of halide that's produced in this case is about the same than that we get when the overburden is 100 times more permeable. And you also see again the effect of the lower permeability. Lower permeability means a less maximum halide. This is the green curve on the right. But also you also see here you have a slightly different behavior in this case, that we have, because of the lower permeability, we do have a relatively short period, and that's the flattened part over here, where only molecular diffusion works. And after that, again, we build up enough of convection cell, and that begins to take care of the problem. Now, let's look again at the total production over here. Which one is the best? Blue curve. What does it mean? This is the more permeable overburden, and that seems to have a better storage capacity than the system with less. What's happening here? Well, we'll come back to this in a second. The next one is the reference case. That's the red curve. The next one is the black curve, which is ejection 5 times the ejection rate. So we inject a higher rate, we reach the maximum pressure earlier, but we cannot store as much. That's what this is telling us. And the worst behavior is basically associated with the green curve, which basically means that it's a lower permeability system. So we have a pretty good idea. Low permeability is not going to be that effective. Makes sense. There is more resistance to flow. The pressure builds up faster because it's lower permeability system. Okay. Now, the very interesting thing is what you see over here. Again, the green curve, which is the one associated with lower permeability, has the maximum amount of dissolved CO2 in the water. So it exceeds 30-something%, which is something very, very good. Now, so the best behavior over here again is reserved for the more permeable system. What you're looking at the right-hand side here is the losses. At the top are the absolute losses. And you can see the blue curve, which is associated with the higher overburden permeability, has the highest losses. But if we look at the composition of the losses, look at this. Let's take the reference case, which is the red case. You see over here, this is the total losses. And there's two components. One is this curve over here with the 2 dots, and that is how much is lost in the gas phase. And the other is down here. It's just a dotted line, and this is how much is lost in the aqueous phase. So you can see most of the losses come from the gas phase, right? Let's see what happens in the case of the higher permeability system. Most of the losses are coming from expelled water. What is happening is we inject, and the CO2 we inject pushes out water. And not only that, pushes out water that has dissolved in it CO2. And this is the reason why this is behaving better. Okay? Because it creates more space for gas by expelling more water. All right? Now, and you can see that over here. Now, in terms of how much, yes, we lose more. In the other cases, in all the other cases, again, we are at 1% or less. In the case of 100 times more permeable overburden, now what we see is that this is, you see over here, it's like twice as much. Still very acceptable. Well, that was intriguing, and I spent probably the last month looking into this. So what we did is, all right, we increased the permeability of the overburden, first by 2 orders of magnitude, then we increased it by 4 orders of magnitude, and then increased it by 6 orders of magnitude. And we see something very, very strange, and I'm still scratching my head. I am certain that the numbers are correct because I tested and retested 3 times all of these things. But I'm trying to figure out what is happening. So, 1 nanodarcy and 100 nanodarcies in terms of total storage is about the same. Then, when we go to 4 and 6, we have a jump. And both of them behave almost the same way. Now we store about 3 times as much gas in the system. With much now the top system, the permeability of the top is 1 millidarcy. That's quite a bit. And the other thing you see down here is in the curve below that the amount that's stored in the gas phase, CO2 stored in the gas phase is very, very low, which basically means that whatever we inject in the system as CO2 dissolves and gets out fast. And you can see here on the right-hand side, which is the losses. They are about the same in the case of 4 orders of magnitude and 6 orders of magnitude more permeability. Okay? And almost all of it, look at the dotted lines over here. Okay, what is happening? All of the losses practically are caused by expelled water. The amount of gas that is being, look at this down here. This is how much goes out in the gas phase. All of it is coming out as liquid. So we expel liquid here, which is much easier to move. Now, keep in mind, when we have gas, we need to build up enough of a bubble to overcome the irreducible water saturation before you can move it. move it. And now it's really easy to move because the overburden is more permeable. So this is what I'm seeing over here. Now, look at this now. Instead of losing 1% or so, we increase the overburden permeability by 2 orders of magnitude. We double this. We increase this 4 and 6, they're almost the same. Still, now we lose about 3.5%. So we're not talking about a isolation system, a storage system. We're talking about a retardation system in this case. So if we store 3 times as much CO2, probably we can live with 3 times as much losses, especially because we have 2 kilometers of profile through which the system can move. Okay. And you can see that over here. What you can see here is, first of all, the water losses. You can see the red is the reference case, T. The one next to it now, the water loss, you can see how much more water we lose in the case of a system like this, where the permeability of the overburden is 100 times larger. When we go to 4 and 6 orders of magnitude larger permeability, look at them. It doesn't make any difference, practically any difference. In addition to this, look at the response when they stop injecting. First of all, the injection time to reach the maximum pressure now is no longer to 22 or 23 or 24 years. It goes to about 100 years, 101 years. Because again, the pressure cannot build up because we keep pushing fluids out. Okay? When we stop, look at the precipitous loss over here. Okay? And again, yeah, we can see this over here. Actually, it goes negative. What does it mean? That basically we have reversal of flow. So some of the CO2 we injected, or the water we injected, goes back once the pressure is restabilized near the wellbore. Now, however, at the same time, what we see happening is that, look at this, this is the amount of salt we have in the system. In the case of reference case T and the one with orders of magnitude, higher permeability, about the same amount of salt. When we go to 4 and 6 orders of magnitude, very different picture. So there seems to be some kind of threshold, at least in my mind. You go over that, it doesn't make any difference. The thing behaves in a different way. The thing, though, is that, talking about a very large amount of salt, okay? I mean, same system. Initially, we start with 2% salt here, okay? And look at what's happening. Go to about over 1,600 kilograms right in the well. That's a lot of salt over there. They're quite close, but they have, again, different behavior. So, try to see what happens in this case. So, here's what's happening. Reference case to the left. This one here is 4 orders of magnitude. This is 6 orders of magnitude. You can see how the gas accumulates. And this is what happens during the rest time. So, goes all the way to the top. Salt accumulation. Here on the left-hand side, this is K4, this is K6. Very, very similar. So I was scratching my head. What is happening? Why was he getting this very different behavior over here? Remember, it's very different behavior. How can they be so similar? Well, during the injection is okay. And then when we try to see what happens in a larger scale, you see these lenses of A-line that form at the top. Okay? And they are quite similar, although in the case of a K6 is larger. Then the rest. You see here in the reference case, the salt keeps decreasing. Here appears to be the same. Nothing changes. So how does it explain the different thing that I saw? Again, the only way we can figure it out is by looking at what's happening on the larger scale. And what you see happening is that this thin lens at the top, that basically keeps, because the area is PR squared, it's much, much larger. This is where you see the decline occurs, which makes sense because this horizontal system is the one prone to dissolution and convection cells. So the next thing we looked is what happens. We have different salinity in the case of the tube well. So what you see here is that if we have a 20% salinity, this is a tube well, What you see happening is that you can accumulate over 3,600 kilograms right next to the well. When we stop, in other cases, you see that they all follow the same pattern. But the more we have, the more difficult it is. But they do decline, okay? Okay. In that case, The very strange thing is, again, we see some kind of, I'm just stealing. There is a good explanation for that. When the salinity is 2% and 5% and 10%, the total amount that's stored is the same. Very, very small differences. What is different is that the higher the salinity, the less you store in the aqueous phase, which makes sense because solubility is less, and you have more in the gas. When you go to 15 and 20%, which is pretty saline system, very saline system, all of a sudden we store more. Why is that? Well, the reason for that is quite simple. Because in that case, we store most of the CO2 in the gas phase, which is what? More compressible. So we can put a little bit more gas there. It's not a huge amount, but it is different. And as you can see, as expected, the higher salinity, the lower the amount that we have in the gas phase, in the aqueous phase. So the black one here is for 20%. We go probably no more than 7-8%. In the reference case, which is 2% salinity, about 25% is in the aqueous phase. In terms of losses, that's another very interesting thing. The higher the salinity, the less the water loss. Okay. I don't want, well, actually, I got excited and I spent a lot of time on all of those. So there is a reason for that. I'll just say that salinity gain has the same type of distribution. You see now that there are lenses now in this case. In the case of X20, which is on the right-hand side, and X10, we are creating these lenses, and these lenses, the globe right next to the well stays there, but the lenses begin to disappear slowly, and that's why we have the reduction. All right. Horizontal tube wells. Actually, I will complete the presentation before showing you all the material that I have, because I think that they overdid it. So what did we do in the case of horizontal well? We did a sensitivity analysis. So what we did, we increased the salinity from 2% to 20%. And we also increased the injection rate by a factor of 10. Well, what we see is something consistent with what we saw up to now. Number one, still no precipitation, even with 20% salinity as opposed to 2% salinity. Number two, the higher injection rate, you see this here, is associated with a lower amount of CO2 in the system. Okay, we build the pressure much faster, but we inject less over there. And the higher the salinity, the higher the amount that it is stored in the system. Again, because most of it is stored in the gas phase. At the same time, you also see that in this case, the higher the salinity, the lower the amount of losses that we have. Okay. Now, I have to go very fast to the next. What I wanted to, there is an additional sensitivity analysis. Here, what I did was I increased the permeability of the overburden by the orders of magnitudes. That, is the green curve. The red curve is the reference, okay, horizontal well. As expected, same thing as before. We store more gas in the system. And even more interesting is that when we go down to 3 kilometers instead of 2 kilometers, which means the initial pressure is higher, we can increase far more gas. This is what we see. Okay. Now, in this case, of course, what we see happening is that because the permeability of the overburden is higher, we have larger losses. But at the same time, we have significantly more stored gas in there, and the larger losses we have do not exceed 1.5%. So again, very, very acceptable. I have 5 minutes, so I will go very, very fast with the rest. This is just to show you that when we use a L well, long well, open to the bottom, after about 1,000 days, 1,042, which is less than 3 years. So what we have is that the hydrate saturation along the well has reached the halide saturation has reached 95-99%. And the permeability has dropped by 6 orders of magnitude. So generally speaking, L wells are good enough for low salinity They are terrible for our salinity. Yes, Strato, I'm rushing. Now, the other thing I want to show you is what happens to salinity when we have a LAR well, which means the short interval. You can see now that if we have low salinity, we have a long period of molecular diffusion, and then it can go down to zero, but it can take 80, 90 years or something. And you reach a certain point like here, like 20% salinity or 15% salinity, you have to wait 100 years before we can, before that the salt decreases significantly. And the other important thing in this case is that, again, the higher, unlike the case of T well, which basically means that we were practically insensitive. 5% salinity, 2% salinity, and 20% salinity, they were very, very close in terms of sequestration, didn't have any effect. That basically means T wells are performing pretty well. Here we have the opposite situation. That basically means with our wells, the higher the salinity, the less you can store in the system. So for 2% salinity, you can see in this case, we can store about 1.2 e to the 8. And if it's 20% salinity, you're going down to 0.65. So significantly less than half, okay? Unlike the T well, which performs actually almost insensitively, insensitive to salinity, here we do have these problems, okay? I will not discuss this over here, other than to say, if you try to rely on the natural reservoir water, aquifer water, to come back and dissolve that amount that we have, you got another thing coming. It doesn't work. And if you try to inject water in order to dissolve the salt that has already been created around our well, what you can see happening is that that injection can last at best, let's look at this over here, in terms of seconds, anywhere between 800 seconds to 900 seconds to 1700 seconds. That basically means that you cannot inject and dissolve it. The only thing you can do is you can just drive the pressure very, very high. The only possibility is to inject after only 45 days. And you can do two things. Either you can inject continuously at the same rate or inject for a very short time. What we found out is that injecting for a very short time is very, very effective. You can do that. And in essence, you can inject far more than you could inject without any, even with a 2% salinity. Because in that case, instead of 18 years, we keep injecting for 27 years. So I don't want to spend any more time on this. Oops, why I'm going down. Okay. So we can see that over here. What happened is that this is the blue case over here. We injected only for 45 days. And the reference is down here, and we went all the way up to here. So almost like 2.5 times more by pre-flushing the system with fresh water. I'm rushing now to the conclusions. CO2 sequestration in saline aquifers is technically feasible if confined by a sufficient low permeability upper boundary, and then you can store large amounts of CO2. In vertical wells, an increase in salinity leads to an increasing and significant halide precipitation in the vicinity of the injection well, but the effect of this on sequestration is a function of the well design. If we have a horizontal well, great, no halide precipitation. Horizontal wells, in terms of storage and overall performance, have clearly a superior performance, and that should be the choice, the main choice. If we have a vertical well, the configuration of the well in terms of the location of the injection interval and the length of the injection interval has a significant effect. Now, what we saw is that even a 2% salinity creates a significant amount of halide. However, in the case of T wells, this is not an issue because they can accommodate them. They're practically insensitive. They're very limited. They have limited sensitivity. Actually, what we saw is that we have a slight increase in the stored amount for higher salinity, like 15 to 20%. Okay, T wells are significant, have significant advantages. Okay, if we have injection at the base of the aquifer, it's okay. And a long well, it's okay if you have low salinity. However, if you have even slightly higher salinity, then they're basically worst performing ones. So probably they should not be considered. We thought that injecting at the base of the aquifer with a limited interval would be probably the best choice. It isn't. It is better than the L well, but significantly less worse performing than the T well injection at the top. The amount of the dissolved CO2 always increases, which is an important aspect of what we do, increases during the storage. And we want to maximize this because, again, the aqueous phase is a significant reservoir, which we need to exploit as much as possible. And it's another case where the horizontal wells have a very significant advantage because they store a huge amount, up to 60% of the injected CO2 dissolved in the aqueous phase. We already discussed how the halide precipitation is basically addressed, is dissolved over time. What are the various, the three phases, the initial dissolution because of the water flowing back, then the molecular diffusion, final, the convection cells. If we had, well, we did not have time to discuss this in detail. But what we're saying is that the effects of high salinity and halide accumulation in the case of our wells cannot be mitigated by waiting for this to be dissolved in native water. It's not going to happen. And it cannot be mitigated by injecting water after we have built the halide, because then you just build the pressure and that's it. You don't basically dissolve it. What you can do, however, is that you can inject. You can pre-flash the system for a short time. In this case, the effect can be spectacular in the case of our wells. Finally, in wells, the performance increases with larger overburden permeability. Yes, I mean, I'm stunned by this, but I stand behind my results. An increase in aquifer permeability, decrease in injection rate, and this is what we have in the case of T wells, which are relatively insensitive to salinity level, and horizontal wells, again, the best performance. The sequestration increases with a larger overburden permeability, as we saw consistently in both cases. An increase in salinity, a decrease in injection rate, and of course, an increase in aquifer depth. As for the aquifer depth in the case of T wells, it's still running. And with this, I would like to conclude. If you have any questions, I will be delighted to answer. Please be gentle.
This has been very enlightening. Let's thank Professor Moridis.